Continuing with our law theme, we have the combined gas law.
Okay, so we've dealt with the ideal gas law a fair amount now. We've used it, a couple different applications. And so what we want to do is then kind of look at what else we can use for it. And one of the things we want to look at is how it relates to the other gas laws, right? Boyle's, Charles, that had those names in front of them. And so what we can do is we can think about rearranging the ideal gas law, right? We have this equation. We could rearrange it such that we have R on one side and everything else on the other side, right? PV and T. So the reason why we would do this is that R is a constant, right? R never changes. PV, N, and T are just variables, right? They're your pressure, your volume, your moles, and your temperature. And those can change. Those can be dynamic depending on the state that your gas is under. But R is always the same. And so if you have R, that never gets a subscript. It never becomes a 1 or a 2 because it's always the same number. But everything else could get a subscript. So what you do when we rearrange this equation like this, we know that it doesn't matter what condition you're in. Are you in state 1? If you combine your pressure and volume, multiply those together, and divide by the number of moles and the temperature, you're guaranteed to get R. If you change it to state 2 and you combine in that same way, you'll still get R as the answer. If you change it to a third state, you'll still get R as the answer. So it doesn't matter how we change our state. If we combine our variables in this way, we'll always get the same constant, which is how we can get the relationships between the variables for two different states. The purpose of thinking about the ideal gas law in this way is to enable us to look at more complicated changes to a sample of gas. Boyle's law, Charles's law, they always had restrictions, right? You needed pressure constant or temperature constant. And in a real change of a gas, you don't always have those things constant. In fact, it can be difficult to maintain those as constant factors. So let's think about just a sample of gas changing. Because when we arrange ideal gas law, it's always equal to R, which is a constant, we know that this combination always gives us the same value. So we can put 1s on all of our variables for ideal gas law. So we have P1, V1 divided by N1, T1 is equal to P2, V2, N2, T2. But it's a sample of gas. So that would imply it's a constant number of moles, which means that the two N values are the same. And this isn't that hard to control, right? You just have some gas. You're not adding any more molecules. You're not taking any out. So that N is going to be constant. So before the change happens and after the change happens, N is just a constant. We can do a substitution there. You'll note that's the N1 right in there. That N1 is showing up then on both sides of the equation. We can cancel it out, right? It doesn't matter. It's on both sides. So P1 times V1 divided by T1 is equal to P2 times V2 divided by T2, right? We basically, all of our other variables are combined except the N. This is called the combined gas law. And the combined gas law describes unrestricted changes of gases, right? The only thing that is held constant is the number of moles. So you have some gas and it changes in a way. Its pressure can change, its volume can change, and its temperature can change. That's a more kind of realistic or applicable relationship when we're dealing with any sort of sample of gas, right? We can't always hold the temperature exactly constant. We can't always keep the pressure exactly constant. How are those things dynamic? How are those things changing? And how can we predict what that's going to cause all those variables to change? Let's apply it. A typical scuba tank has 13.2 liters of air at 153 atmospheres. Standard water temperature is 27 degrees Celsius. What volume of water is available to a scuba diver when the water pressure is 3.13 atmospheres and her body temperature is 37 degrees Celsius? All right, so this would be, basically there's air inside of that tank. And a reasonable question would be, when this person is breathing it in, how much air is available for her to breathe? That seems like an important thing when you're filling up your scuba tank. Exactly how many breaths can you take of that air? And so this is a closed sample of gas, right? That air goes from the tank into her mouth, and so she can breathe it in. She doesn't want to waste any, right? She doesn't want to lose any of that mass, any of those moles. And so we can see that what happens is you have this change where your tank is, you have 13.2 liter tank. It's under quite a high pressure and it's in the water. So it's at that temperature of the water. And then that air changes, goes into the pressure that she's experiencing from being in the water and her body temperature. And so that air is changing in a lot of different ways, going from the tank into her lungs. And so the question would be, what is the total kind of new volume that air would be accessible in her lungs, right? That would be available to her to breathe. So this would be really the kind of case where we have a lot of changes, but we don't have anything about the number of moles, right? We can actually figure it out if we really wanted to, but we also just don't have to worry about it. This would be really a case where we can use the combined gas law. So if we want to walk through it kind of in our process, what do we want? It's volume of air for the diver, right? So volume of air for the diver is what we want, and we're given a ton of information, right? We have the 13.2 liters, we've got a couple different atmospheres, a couple different temperatures. So one of the things we can immediately see that this goes back to that initial named gas law. We want a volume and we're given a different volume. The difference is we want volume for air for the diver and we're given the volume of the tank of air. So that's air in just a different kind of state under a different set of conditions. Again, there's lots of variables that are changing. This is a sign we're dealing with a process. We're going to have subscripts on our variables, 1s and 2s. And because we have so many variables, that's where we're going to need to use the combined gas law. We do need to be sure that moles are remaining constant. Again, you can generally just assume that as long as you're just changing temperature and pressure, you're not changing like how much gas there is or putting any in or taking any out. So you're in pretty good shape. You're looking at combined gas law. So P1V1 over T1 is equal to P2V2 over T2. There's a lot of variables here. So it does become, you want to be careful with kind of assigning the different variables, but in general, we're probably in pretty good shape. And when we're doing this, the 1 and 2, we're just going to say everything associated with the air in the tank, that's going to be my 1 state. And then everything associated with the diver is going to be my 2 state. We want to solve it. We start with our combined gas law. We want V2, and we have this huge list of variables. Again, tank air is 1. So basically the tank, we're explicitly told 13.2 liters and 153 atmospheres. We then do kind of have to know that the tank is in the water to know that that's the temperature of the air inside of it. But, they're kind of all listed together. That's that information. And then everything else is going to be for the diver. So the diver's in the water, so she's experiencing that pressure, and her temperature of her lungs are in her body. So that's going to be the temperature of the air inside of there. So again, those are the associated with that. So we can go ahead and plug all of those variables in, right? The pressures and atmosphere, liters, Kelvin. Again, like when we were dealing with the Boyle's law and named laws, you can use any pressure unit as long as they're both atmospheres or both bar or whatever it is. Make sure your temperatures line up. They do need to be, that is one thing, still in Kelvin. So I went ahead and added the 273, converted those into Kelvin. We can rearrange the equation to isolate the V2. So I just divided the 313, multiplied the 310 Kelvin. When we look again, atmospheres need to cancel out, Kelvin need to cancel out. And what we're left with is that the volume is 667 liters. This is a reasonable calculation to want to know. If someone gives you an air tank, you want to think about how much actually can you breathe of that. You breathe about 2 liters, so that's about 300 breaths. And so, you got a decent amount of volume in there when you're breathing that in. Good, a thing to want to know of how many breaths can you take from this air tank that you're going to be, surviving off of in your scuba trip. Participation 629, question 4. Helium gas is in a 1.0 liter container at 100 K and 0.5 atmospheres. The gas is compressed to a final volume of 0.75 liters, and the temperature of the gas becomes 120 K. What is the pressure of the compressed gas? This is the 4th question on participation 629, due Monday, June 29th at 11:59 p.m. over on Blackboard. The link to the assignment is right below the links to these videos. Again, helium gas is in a 1.0 liter container at 100 Kelvin and 0.5 atmospheres. The gas is compressed to a final volume of 0.75 liters, and the temperature of the gas becomes 120 K. What is the pressure of the compressed gas? So the ideal gas law, this sort of rearrangement that we're using to build up the combined gas law. we can actually use it to come up with any gas law we were doing, even the more constrictive ones, Boyle's law and stuff. So, for example, a sample of gas, so that would mean your N's are constant, undergoes a process that changes the temperature and volume, but not, or sorry, the pressure and volume, but not the temperature. So your two T's are also constant, not just that. So now we can see that you end up with NT on both sides, and those can cancel out, and you get Boyle's law, right? So by taking this very general expression that's true for any ideal gas and applying restrictions to it, you can come out with Boyle's law. Similarly, a sample of gas undergoes a process that changes the temperature and volume, but not the pressure. Now those cancel out, and we end up with Charles's law. So we can see that the reason why all of those laws existed was because of the ideal gas law that's underlying all of those gases, that is explaining or describing for the different states. Constant, a sample of gas, the volume doesn't change. That's Gay-Lussac's or Montan's law. We didn't talk about too much, but it works in the exact same way. N and V cancel out, simplify your equation to only be about pressure and temperature. That's it. 4 questions on participation 629. You want to find all 4 of those questions, get them answered, and get those answers submitted over on Blackboard by Monday night. On Tuesday, we'll have the final set of videos, 6:30 participation. On Tuesday morning, we'll do the Chapter 7 participation quiz. Again, that's only covering the participations from 625 and 626, the Chapter 7 stuff after Exam 3. On Tuesday, we will then do the molecular modeling activity class lab. There's a pre-lab for it, but not much. Or that no, there's just a pre-lab. There's no notebook, no technique. And then we'll do it on campus on Tuesday. And then the lab technique presentation is follow the schedule for on campus, and the video is due Wednesday. And the final exam is Thursday, and then that is it for the class. If you have any questions about anything, don't hesitate to reach out. There will be the answers to the participation that go live Monday night. Otherwise, that is it for me. One last set of videos tomorrow. One last time of doing lab on campus tomorrow. Bye-bye.